In this video, we'll talk about backpropagation. Before we get to backpropagation, let's talk about batching. Batching is the process of combining the vectors of several data points together into a matrix and passing this all through the network at the same time. So for example, if you look here, then we have the vectors of two data points. We have x1 here and x2 here. And both of these are multiplied with the same weight matrix, and they get their own output vectors. So this is the output of data point 1, this is the output of data point 2. And what we can do is we can combine these inputs together. We can stack both of these vectors into a matrix and then multiply it with this same weight matrix. This is the output that we get. Now, you can see that the outputs that we got when we were doing it for each input vector independently are the same as the outputs that we get when we batch our inputs together and do it together at the same time. And this applies to all the main neural network operations, so adding, subtracting, doing element-wise multiplication, matrix multiplication, also applying activation functions. So you can batch your data points together and send them through the network at the same time, and you'll get the correct output as long as you have set up your network correctly and you're using the correct dimensions in your matrices. And why would you want to do this? Reason one is that GPUs are much more efficient when working on matrices as opposed to vectors. So when you're doing matrix multiplication, then the GPUs are able to parallelize these large operations. If you're instead doing just vector multiplication, then you're going to be spending most of your time copying vectors to the GPU, and your whole network training is going to take longer. And another reason is actually regularization. So we'll see later in this lecture that if we're optimizing our neural networks, then it can be beneficial to combine updates from several data points together. And this becomes easy with batching. You calculate the gradient based on your whole batch as opposed to an individual data point, and that makes the updates to your network more stable and more accurate. And now let's see how we can calculate a full forward pass through a multi-layer neural network. Here we have an input matrix X, and this is now a batch of data points. The matrix has dimensions of n by k, where n is the number of data points in our batch, and k is the number of feature vectors for each data point. We then give this matrix as input to the first layer in our neural network. So this is a linear transformation. It applies a weight matrix and it adds a bias, and then we get this output z. This z then goes as input to our activation. We apply this activation function here and we get a, which is the output of our first layer, first hidden layer. And this keeps going. The output of this layer now goes into the next linear transformation. We again apply an activation function. This goes into another linear transformation, and at the very top we have the output layer, and there we apply the activation function that we want for our output. And finally, we calculate the loss. So this is the loss score that we previously discussed, and it determines how well our model is performing. Now, when we're training our model, then we want to update our model parameters. and we want to update all the parameters throughout this network. So these are all the weight matrices and all the biases. So these are all the parameters that we want to update. And we can do this using gradient descent, but if we just do it naively as we did with linear regression, then this is going to be a huge amount of calculation. We have to, for example, in order to calculate the weight matrix, the partial derivatives for this weight matrix here, we have to go through all the functions in the network, do all the calculations for each of the parameters there. And we don't want to do this. There's an easy way, and it's called backpropagation. So the idea of backpropagation is that we can break these calculations down. We can calculate the partial derivative at a particular layer, let's say over here, based on the partial derivative of the next layer. So we start at the very top, we calculate the partial derivative of the loss with respect to the output, and then we use this to calculate the partial derivative of the loss with respect to the last hidden layer. Then we use this to calculate the partial derivative of the loss with respect to the first hidden layer. And finally, we can calculate the partial derivative of the loss with respect to the input as well. So we don't have to do the full calculation each time. We kind of break this calculation down and move through the network in a backwards direction. So our forwards pass starts from the input and moves to the output. Our backward pass starts from the output and moves to the input while calculating these partial derivatives. In order to calculate all the necessary partial derivatives in our network, we make use of the chain rule. And the chain rule says that if z is a function of x and y is a function of z, then we can calculate the derivative of y with respect to x by calculating the derivative of y with respect to z and multiplying that with the derivative of z with respect to x. And that means we can break the derivative calculation down into smaller steps. For example, let's say we want to find the partial derivative of the loss with respect to this weight matrix here. And that is something that we need in order to do a gradient descent update step for that weight matrix. So the partial derivative looks like this, and we can break it down by finding the partial derivative of the loss with respect to z, where z is the output of that linear transformation, and multiplying that with the partial derivative of z with respect to the actual weight matrix that we're interested in. Now, how do we find this part here? Well, we can break this one down as well. So we find the partial derivative of the loss with respect to a, where a is this output of the activation function here. And we multiply it with the partial derivative of a with respect to z itself. And we can keep breaking this down until we get this whole sequence of operations over here. And if you look closely, then you notice that there's a certain repeating pattern happening there. So there's two types of partial derivatives here. One is the partial derivative of the output of an activation function with respect to the input of that activation function. So these are the green boxes here. And the other one is the partial derivative of the output of a linear transformation with respect to the input of that linear transformation. So these are the blue boxes here. And then at the very top, we have the partial derivative of the loss with respect to the output. And then at the very bottom, we have the partial derivative of the output of the last linear the first linear transformation at the very bottom of the network with respect to the weights of that linear transformation, and these are the weights that we are trying to update. So these are the same weights. Yeah, so this is essentially what we use to calculate partial derivatives, and this is the essence of backpropagation. However, don't try to directly apply this whole formula to calculate your partial derivatives. That's because there's a little bit more going on here. This is a slightly simplified version. So the partial derivative of a matrix with respect to another matrix is actually a four-dimensional object. This object contains the partial derivatives of every element in the first matrix with respect to every element in the second matrix. So this one here, for example, is a four-dimensional object. And you don't really want to be calculating four-dimensional objects or making operations on them. So we actually can simplify this down a bit so that we can still work with two-dimensional matrices, and the operations are much more easier to handle. Here is another view of backpropagation, a more graphical representation. Let's say we have this linear transformation z equals x times w, and then during the forward pass through our network, this operation takes x and w as input, and it produces the output z. And then during the backwards pass, it takes the partial derivative of the loss with respect to z. So we just assume that it comes from somewhere, that it's calculated by the upper layers. We take this as input into this node, and then based on that, we can calculate the partial derivative of the loss with respect to x and the partial derivative of the loss with respect to w. And this is all there is to backpropagation. We just iteratively keep calculating the partial derivatives, taking the existing partial derivatives from the top layers and passing them on downwards. So for example, this one we calculate so that we can pass it down to a lower level that needs it to calculate its own partial derivatives. And it's worth noting that we changed the notation on these slides. In the last lecture, we were working with column vectors. So we assumed that x is a column vector. So our operations look like this. Here, when we're working with batches, we have changed to this kind of notation. So now we are assuming that the input vectors are row vectors, and they are stacked on top of each other into a matrix. This just simplifies what the equations look like and makes our calculations a bit more clear, but the end result is exactly the same. It doesn't really matter how you structure the matrices as long as they give the same output. And just for reference, in case you want to check that everything works out and all the dimensions match, then I've included the dimensions of each of the matrices here on this slide as well. Okay, let's work through an actual practical example of backpropagation and find what the more convenient form of backpropagation looks like. In this case, we have a linear transformation, z equals x times w plus the bias b. You can see the dimensions of all of the matrices here. And we can consider a particular case. So let's actually give these matrices particular instances. So this is what they would look like. We have a 2 by 2 X matrix, a 2 by 3 weight matrix, and a 2 by 3 bias matrix, which is actually just the bias vector repeated twice because each neuron in the layer only has one bias, so one real valued bias. So these are contained in this bias vector, and then we just have to stack it because we add the same bias to each input vector. And if we do this operation, then the output looks like this. So this is all the values that we would get in matrix Z. Now, first of all, let's assume that we already get the partial derivative of the loss with respect to this output Z. So we get it from somewhere else, from an upper layer. The shape of that partial derivative looks like this. First thing you can see is that it has the same general shape as Z itself. So here Z has 2 rows and 3 columns. Same applies here for the partial derivative. And each element in here is the partial derivative of the loss with respect to the corresponding element in Z. So that's a general tip for you, that the derivative of a scalar with respect to a matrix has the same shape as the original matrix itself. Now, if we want to update our weights in this linear transformation, then we need two different partial derivatives. We need to find the partial derivative of the loss with respect to the weights, and the partial derivative of the loss with respect to the bias vector as well. And then in order to pass the partial derivatives or pass the gradient down to a lower level, we also need to calculate the partial derivative of the loss with respect to the input. So this is what the lower level will expect, so that it can calculate its own partial derivatives. Using the chain rule, we can break all of these down a bit. And you can immediately notice that there's a familiar component in all of them. So it's the partial derivative of the loss with respect to the output of that linear transformation. And lucky for us, this is the thing that we assumed that we already have. So we're going to need that for the calculation of all of these other partial derivatives. But there's a little bit on top that we need to do in order to actually find the real values for all of these derivatives. So we'll get to that next. Now let's focus down even a bit more and look at only one particular element in X. So let's look at x11. Let's try to figure out how to calculate the partial derivative of the loss with respect to that one particular element. So that's the equation here. Now, if you look at the equations for the forward pass of the neural network, then you can work it out that this particular element affects exactly 3 values in the output, Z11, Z12, and Z13. So this is the equation that we get for the partial derivative of that element. And this is actually already using the chain rule. So the weight here comes from the fact that this is a partial derivative of Z11 with respect to x11. So intuitively, this element x11 affects the loss in a way that is determined by the weights that it multiplies with, so these 3 weights here, and the loss of whatever uses this element. Now let's work our way back up from an individual element to the whole matrix of X. So this is the equation that we found for the partial derivative of the loss with respect to x11. If we do this for all the elements of x, then this is what we got. So this is the partial derivative of the loss with respect to the full matrix x. And if we look closely at the values here, then we find that we can actually break this down into a matrix multiplication. So this matrix, this whole matrix, is equal to the multiplication of this matrix and this matrix. And so this is a dot product between the two matrices. These two matrices should look kind of familiar to us because this one here, the first one, is the one that we assumed at the very beginning that we have as input. So it is the partial derivative of the loss with respect to z. So we get that from an upper layer. This one is just the weight matrix for that particular layer transposed. So we can write it like this. And that's the simple way of calculating backpropagation for our inputs x in a given layer. So this is one of the important formulas for backpropagation. In some networks, we can actually use this to update the inputs themselves. But in most cases, what we do is we pass this partial derivative down to the next layer below this current layer, and then they get this as input and they calculate their own partial derivatives for all the parameters that they need to. Okay, so now we can calculate the partial derivatives with respect to our input, and this allows us to pass the gradient down to lower levels. But what about the weights? We need to calculate the partial derivative with respect to our weights in that particular layer because we need that to actually perform the gradient descent step. And we can do basically the same process for the weights. So if we break it down for one individual weight, in this case W11, then we get the equation here. One particular weight, in this case, affects two values in the output. One weight only affects one neuron, but because we have two data points in the batch, there are two values that are affected. So it's the same neuron for two different data points. And if we do this for the whole weight matrix, we can again break it up into two parts, into a dot product of two different matrices that look like this. And once again, these are familiar matrices to us. So this one here is again the partial derivative of the loss with respect to z, which is the one that we assume that we get from an upper layer. And then this one here is X transpose. So it's the input matrix, the matrix of features that we give as input to our layer, just the same matrix transposed. We multiply these together and we get the partial derivative of the loss with respect to the weights in that layer. And finally, we need to consider the bias as well, because when we are performing a gradient descent step to update our model parameters, then we need to be updating the biases of all the layers as well. And for that, we need to calculate the partial derivative of the loss with respect to the bias vector. And again, if we use the same derivation as we used before, what we get is that this is equal to a column vector of ones transposed, so it's a row vector of ones, times the partial derivative of the loss with respect to z, which is the partial derivative that we assume that we are getting passed down to us from an upper layer. But I will leave that to you to do this derivation and to figure out why this is a column vector of ones that we are using here for the bias updates. Just as a reference, I've included a slide on partial derivatives for vectors and matrices. So these are kind of general rules for applying partial derivatives to vectors and matrices. You don't need to memorize these, but it can be a good reference when you're trying to work out and understand what is happening in the derivation of the backpropagation update rules. Now that we can calculate partial derivatives with respect to all parts of our linear transformation, there's only one component that's missing in order to perform a full backpropagation through our multi-layer neural network. And that's how to handle activation functions. Now, activation functions are generally applied element-wise. So we can write them out like this. So here we have the activation function itself. We have the input matrix to an activation function and the output matrix of an activation function. And because the function is applied element-wise, we can just write it like this. So the function g is applied to every element in Z to get A. Activation functions themselves generally don't have any parameters that need to be updated during training. So all we need to do is we need to pass the gradient through the activation function correctly so that the backpropagation can continue. And for that, we need to calculate this value here. So this is the partial derivative of the loss with respect to the inputs to the activation function. We can break that up into two parts like this. And for a single element in Z, for Z11, this equation looks like this. Now, if we look at this part here, then this is actually the regular derivative of the activation function, because the activation function doesn't take any other parameters as input. So we can write it out like this. Now, we can generalize back to a full matrix. So now we find the partial derivative of the loss with respect to the full input matrix Z. We can write out the values that we have found, but now for each element of Z. If we look at this matrix, then we can see that we can actually break it down into two separate matrices again, as before. However, importantly, this operation here is no longer dot product. So in this case, in the case of activation functions, this is an element-wise multiplication. We apply an element-wise multiplication to these two matrices. And if we look at the matrices, then again, they look familiar to us. So this is just the partial derivative of the loss with respect to the output of the activation function. This is just the derivative of the activation function itself, given Z as input. This generally applies to all element-wise activation functions. The only thing that differs is this derivative over here. So where do we get this derivative for our particular activation function? Well, we get it from this table over here. So I've included the main activation functions that we use in neural networks over here. We have the linear activation function where the input is just equal to the output. The derivative of that is 1. Then there's the sigmoid activation function, and the derivative of that has this nice form that it can be defined through the sigmoid activation function itself. So it's just the sigmoid times 1 minus the sigmoid. Similarly with tan h, the derivative of tan h is 1 minus tan h squared. And for ReLU, the derivative is 1 if z is greater than 0 and 0 otherwise. Most of the activation functions that we looked at, we apply element-wise. And the one exception to this is softmax. For softmax, we give a whole vector as input, and we also get a vector as output. So for example, here we are applying softmax. We take a vector zi as input, so this is a vector for data point I. And we get a vector of predictions as output from softmax. So this is going to be a probability distribution. And softmax is usually combined together with the cross-entropy loss function. So we have a neural network. At the very top output layer, we have the softmax activation function. And then on top of that, we put the cross-entropy loss and optimize that in order to train our model for classification. Now, the backpropagation of partial derivatives through softmax and also through cross-entropy is quite involved. It requires a lot of math, and you're welcome to do the equations yourself or find some proofs online. There are many available. But for our purposes, we're going to simplify this a bit because if we combine softmax with cross-entropy, then the joint partial derivative through both of them has a very nice form. And you can see that here. This is the partial derivative of the loss with respect to the inputs of softmax. So we've gone through both cross-entropy and softmax as well. And this is just the predictions from our model minus the true class labels and divided by n if we are normalizing our loss by the number of data points. And just to clarify that the YA here is a vector because softmax gives a vector as output, which means Y itself, both of these Ys actually, are matrices. So they are batches of vectors. The Y hat here contains the predictions. So these are vectors of probability distributions with values between 0 and 1. The Y here is the matrix of true labels, and it only contains zeros or ones. So it's going to be mostly zeros, but it's going to have ones in the position that indicate the correct class for that particular data point.